All right, like I said, I'm gonna go over this. And I'm trying not to be too fast on this, but these are friction notes. So what I'm gonna talk about in more detail is friction, which you already know that I've talked about as far as being part of net forces and so forth. All right, so we've got two types of friction though. Do you remember the two types?
Kinetic.
Yeah, kinetic and
Potential.
no, static. Okay, and static is basically friction that holds an object to a surface. Kinetic is the friction that basically impedes the motion while it's moving. All right, so now we're going to talk about what makes friction happen, and there's an equation related to that and a coefficient that relates to that depending on the interaction and such. So if I have this Kleenex box, so what's happening with friction now? In order for there to be friction, what has to be happening between two objects? There has to be
Motion.
no.
Force forward.
In order for there to be friction, the two objects have to be,
Touching.
yeah, that's right, in contact with each other. Okay, so only way you'll have friction. All right, so being in contact with each other, it's going to be a function of what?
Weight.
Yeah, gravity is it. Now, gravity is part of it, but not the actual thing that's going to be causing the friction. What is preventing the object from accelerating downward? Well, what's the table doing to it? Yeah, no, not slowing it down. It's normal force, right? It's pushing it back. So there's a normal force that's going on to it. We're going to make a correlation between friction and the normal force, all right, and so forth. So we also have to look at from the standpoint that, now the gravity is on it right now in this situation because it's level. Now the moment I turn it at an angle, all right, what's gravity now doing? But is the box moving? Well, it's not moving, is it? So there's clearly static friction that's involved here. But now what is gravity doing? It's now doing what two things?
Still pushing them.
Yeah, it's pulling down on the surface and creating the normal force, but it's also now doing what? There is a now force acting in this direction to have it go down the ramp if it was frictionless, but it's being countered by static friction going in the other direction, all right? And so what are the dynamics that's that's involved there? All right, so that's kind of one of the things we'll look at as we kind of move through this. Friction, resistive force acting between materials that tend to oppose or dampen out motion. That's already what we know the definition of friction is. We talked about the two forms of it. There's static friction, frictional placed on body at rest. Force placing body at rest into motion. Typically you see it on an incline, all right? Kinetic friction, frictional forces tending to slow down a body in motion, all right? So basically the object is moving when there's kinetic friction, all right? So friction results when two surfaces are pressed together closely, causing attractive molecular forces between the molecules, the two different surfaces, and this one coming up as the bigger of the one. Friction depends upon the nature of the two surfaces and upon to the degree which they are pressed together. So the big thing that we're looking at here, equation-wise, is the force of friction is going to equal mu times the normal force, okay? And mu is called the coefficient of friction. This is the Greek letter mu, the lowercase Greek letter mu. It is not a U with a tail. So in addition to using second law for friction, which we've used kind of before, we can also now use the coefficient of friction because it's tied to the normal. And that's why you see the normal force here. Kind of a strategy is you find the normal force, you know the coefficient of kinetic or coefficient of friction, you're able to find the friction force, can't you? All right, and it will depend. It will depend on, like it says, the intermolecular relationships between those kind of components. All right, this might work. Are objects made up of different materials? Well, the obvious answer is yes. So if I tilt this, I don't know if this will work. No, that's down there. I've got the remote and I've got the Kleenex box. All right, will they go down at the same time? Well, I've tilted it, but neither are still moving. Okay, and what's going to happen is now the remote has started moving, but the Kleenex is not. Why? Because they're two different surfaces. The surface of the desk is the same, but the plastic made up of this probably smoother, and the cardboard made up of this is probably a little bit rougher, which is going to cause less friction in here, less static friction to overcome. That's why the remote will move first. All right, so everybody get that concept. So the coefficient is going to be representative of the interaction between two types of surfaces, two types of materials, and so forth. You get in the engineering realm, they'll talk a lot about when friction is involved in things, what's the coefficient of friction with these kind of things. And they'll need to know the coefficient, because if they have two entities acting within each other, that coefficient is going to be dependent on how something may function. If they want friction, they'll want something with a greater coefficient. If they don't want much friction, they're going to want something with a smaller coefficient. All right? So that's the importance of that equation related to friction. So coefficient of friction, the resistance of sliding of two surfaces in contact with each other. Usually the coefficient of friction when the object is stationary is slightly larger than the coefficient when the object is sliding. It's harder to get an object started, all right? So the static coefficient is going to be greater than the kinetic coefficient. Case in point, anybody ever moved an article of furniture across a floor? I think many people have, all right? And if you have, you'll probably note that if I was to move this desk, all right, or a heavy couch or a heavy piece of equipment, and I want to slide it across the floor, and you look at it, it's pretty heavy, I might be able to do it, or me and a buddy might be able to do it, but you notice that you're going to push really hard at first. So I'm pushing on this desk with some force right now. It's not moving though yet, is it? As I push a little bit more, okay, you see it start to slide, but as I'm pushing more and more, it's harder, but now once you get something moving, is it easier, is it harder? It's easier. That's why when people move or slide something, once you get it moving, this is a way lot easier. Why? Because the static coefficient is greater than the kinetic coefficient. All right? And so if you ever move something, make a decision first. I need to get this couch or this refrigerator from here to there, strategize it, and or if you get help, when you initiate it, go and keep it sliding until you get to that spot. Then you've minimized the work, haven't you? Don't stop, go, change directions. Because every time you stop, you're going to have to reload and overcome static friction. And it creates more and more forces or energy. All right, so we see that concept. You've probably experienced that in some way. So over the weekend, go find your refrigerator and pull it away from the door. All right, go move your refrigerator around. You'll kind of feel how easy it is. Once you get that refrigerator moving, it's easy to slide out of there, isn't it? Yeah, I'm telling every class, go move the refrigerator. Tell your parents. Lambert Physics said, go move the refrigerator. It's a physics experiment. So I'm just kidding. Do it somewhat carefully, but yeah, don't do it unless you're careful. Now, where should you put it? Pull lower or higher? Lower. You want to stay below the center of mass. You go above the center of mass. And you push high in the refrigerator. What's going to do? Tip over. Right. We'll talk about center of mass things maybe down the road. So yeah. When you move and when you're dealing with friction, make sure you put some intelligence behind it. Make sure you understand, if I need to move something, I've got to overcome friction. Or I've got to manage friction. And that's kind of how you do it. All right. Any questions on that? Anything? All right. So, which requires more force? Pulling a box horizontally or pulling a box at an angle? Now, this is a pretty good one. If I want to pull something, all right, and if I was down here and I applied 10 newtons of force straight parallel, all right, I've applied the force and it's overcome friction, hasn't it? Okay. However, if I apply the same 10 newtons at an angle and I do this, okay, it's sliding. So which is harder, pulling it straight horizontal or going to an angle and pulling? Well, what's the free body diagram doing when it's perfectly horizontal? Here's my applied force, which is perfectly parallel to the ground, and I still have the normal force, right? And I still have the force of gravity, and then I will have overcome the kinetic friction, okay? Does everybody see that? And if this is 10 newtons, great. But now what happens if I pull at an angle at 10 newtons, all right? What must I break an angle down into? A what and a what?
X and Y.
X and a Y. So now if I pull the 10 newtons, all right, I'm gonna take, you know, the cosine of it, it's gonna give me this FAX. And let's say this is, well, this would be 8.7 newtons. And then the remaining part is gonna go up there, isn't it? Okay? And so instead of pulling at 10 newtons, I'm now pulling 8.7 along the X. All right? Now, if I was to do that free body diagram, I now have this, which is FAX. I now have FAY, and I still have the force of gravity. That doesn't change, does it? But what am I still, and I still have this friction over here. What does this change? What's missing still? The normal force. And if this is the same as this normal force, now that gets cut down to this, doesn't it? Because now my normal force is decreased and it's replaced by the FAY going up. So in other words, when you pull at an angle, you sort of inadvertently, in a way, made this thing lighter because you've reduced the what? You've reduced the friction. Because you've reduced the what? The normal force, right? You see that? And friction's tied to the normal force. Kinetic friction equals mu times the normal force. If this is 1, and if the coefficient is 1, and my first normal force was 10, right? 1 times 10 is 10, but then I now change the normal force to 8.6. So now it's 8.6 newtons of friction. We've reduced the friction, which means it's going to be easier to move, isn't it? Okay, so it's harder to move it, believe it or not, parallel. You would think, oh no, just now that I'm going up here, only a fraction of my force is going through there. That's true, but we've also reduced the friction. All right, so there's kind of some play in there. Does everybody see that concept? Okay, you got it? I think the problem is next. Yeah, so here's a couple problems, so follow along. You've got 2 sample problems, which you'll have to do right along with me. 2 90-kilogram passengers get in a 30-kilogram sled. How much force will the puller have to exert to move the sled? The coefficient of maximum static friction between the sled and the snow is 0.15. If I was to list my givens on this, my mass equals 210 kilograms. Does everybody see how I got that? 90 plus 90 plus 30. That's what's on the sled, all right? And it also tells me that I have a coefficient of friction equal to 0.15. It's asking me for the static friction, okay? And that's all the information that I have, right? I also kind of still have, you know, acceleration of gravity is still negative 9.8. We still may need that, all right? Now, there's 2 ways. If you need to find the static friction force, you now have 2 ways to find it. You have static friction equals mu times the normal force, but we also have static friction equals mass times the acceleration of the object. You got it? Now, depending on which pieces of information you have is what you can use. Do I need the static friction? So I'm gonna see if I can use this, because it does give me the coefficient. Do I have the coefficient of friction? Yes, I do. Do I have the normal force? I don't. Now, do I have the ability to find the normal force? Sure I do, because if I'm running a free body diagram on this, I've got the normal force up here and the force of gravity down here. The F net along the Y will equal my normal force minus my force of gravity, right? So in other words, this is balanced, so 0 equals my normal force minus my force of gravity. If I find the force of gravity, I get the normal force, don't I? Just opposite direction. So how am I going to find the force of gravity? Second law, force of gravity equals mass times the acceleration of gravity. Force of gravity equals 210 times negative 9.8. 210 times negative 9.8 equals negative 2,058 newtons, if I was to do that right. Let me double check. Make sure 9.8 times 210 is 2058. So cool. So my normal force, which we know is, subtracting that, it's going to be positive 2,058 newtons. Cool. Can I now use my static friction equation? Well, sure I can. That will be my static friction equals mu times the normal force. My static friction is going to equal 0.15 times 2058. The static friction is going to equal 308.7 newtons. Okay, does everybody see that? Is it positive or negative? Or we don't know. Could it be both? In this case, it could be both, because we're not clear, didn't establish which direction is pushing or pulling, does it? If it did, it would matter, wouldn't it? Moral of the story is, when you use the coefficient, it will always be positive. The coefficient is blind to the direction. The direction you're going to need, and the normal force is always going to be positive, isn't it? So a positive times a positive will always, on the calculation-wise, make that positive. But you have got to go back in and change the signage on your own if direction matters here, doesn't it? Okay, if I was pushing this thing to the right, then the friction's to the left, it would be negative. You have to put that sign back in there. You got it? Okay, does everybody see that? All right. Any questions on that? All right. How this works is this, by the way. Before you start pushing on this thing, this is the free body diagram, isn't it? Okay? Before you push on it. However, now you start to push the sled. Let's say I push it with an applied force of 100 newtons, but it hasn't moved yet. What now has to show up on the left side of this free body diagram? Static friction, doesn't it? Because it's balanced, hasn't moved yet. So again, didn't start's not there. The moment I start applying the force, it doesn't move. This shows up and this shows up. And I increase this to 200 newtons, and it still isn't moving yet, because it will move once it gets past that, won't it? Then this increases to 200, doesn't it? Be negative 200, right? I keep pushing, and then once I get to 308.71, what now has to happen? The object will move. When you calculate this, this is the maximum amount that will hold that object in place. You go over that, the object changes to kinetic friction, doesn't it? All right, does everybody see that concept? All right, any questions? Okay, next one. A 1.5 book slides across the table. 5 meters per second comes to rest after traveling 10 seconds. What's the book's acceleration? I have mass equal 1.5 kilograms. I'm going to put that on hold for a bit. I have an initial velocity equals 5 meters per second. A final velocity equals 0 meters per second. It tells me time equals 10 seconds. It's looking for acceleration equals question mark. Am I going to find that through force, or am I going to have to go back into kinematics? Yeah, kinematics, and which equation has VI, VF, T, and A? You've got final velocity equals initial velocity plus acceleration times time. I'm going to plug those in. 0 equals 5 plus 10 times A. Subtract 5 from both sides. We do the algebra on this. This is negative 5 equals 10A. Divide both sides by 10. Acceleration equals negative 0.5 meters per second squared. That's how I get the acceleration. I'm going to need that as I move through the rest of these. What's the magnitude of the frictional force? Once again, I can use frictional force equals mu times the normal force, or I can use friction force is going to equal mass times acceleration. I can use either or. Okay, I need the frictional force. I I can probably get the normal force because I've got the mass, don't I? I can run that through the force of gravity. What's the problem with this one? I don't have the mu, do I? So I can't use that one. However, can I use mass times acceleration? Do I have the mass? Yes. Do I now have the acceleration? Yes. So this one you're going to run through second. So this is the force of friction is going to equal 1.5 times negative 0.5. So the force of friction is going to equal negative 0.75 newtons. There is your answer to part B. All right. What's the magnitude of the normal force? We now know by, of course, a free body diagram that the normal force does this, the force of gravity does this. It's balanced. If I find the force of gravity, I find the normal force, don't I? So I'm going to use the force of gravity equals mass times acceleration of gravity. Force of gravity is going to equal 1.5 times negative 9.8 meters per second squared. What's 1.5 times negative 9.8? It's going to be negative 14.5. So the force of gravity is going to equal negative 14.7, newtons. That means my normal force is going to be equal to 14.7 newtons. All right? Last, can I now calculate the coefficient of kinetic friction in here? Yeah, because I'm going to use the force of friction is going to equal mu times the normal force. The force of friction is going to equal, that's going to be, when I plug this in, my force of friction is going to be negative 0.75 is going to equal, put this mu, got a different color, times 14.7. What do I do to both sides? Divide by 14.7. And mu, you're going to get mu calculated out to equal to negative 0.05. And there's no units to this because it's a coefficient. Now I'm dropping the negative and I'm calling this mu equals 0.05. Why am I doing that? That coefficient has to be positive. Why did the negative show up? Because this friction is going in the other direction. Does everybody see what I did there? All right. Any questions on friction or the coefficient of friction? All right. That is it. All right. In a few minutes, we are going to go head down to the cafeteria and or the gym, depending on what's available. All right. So let's get our stuff and go down there.